answer is yes. She likes changing people's spreadsheets.
Yeah. Well, especially because the Part C, our 3 trials all had different temperatures. So technically, you got to do all the calculations for each one because the temperature's different.
How the hell did we get something changed that much?
It did. We had one trial. They had 19, 20, and 22.
Someone must have had a hot water.
Yeah. Yeah. I mean, I think probably next time we get like a really big beaker that we can just pour it all out of. I don't know.
Cool, I suppose. That's not impossible. Hydrostatics. New lecture. Cool. That's this thing. All right. Anybody any crazy ethics questions before we start, or anything else that's complicated? No? Why? I can't understand. So there's 4 electrical students that are finally going to show up on time.
That many have been missing?
Yeah. Because they were supposed to go to the lab at 9 o'clock and come to the lecture for cons at 10, then go back to lab. But then their National Electrical course appears on their schedule at 9 o'clock, and no one paid attention to that. So then I literally was like, okay, look, we got to get this sorted out. So I just sorted it with Mr. Havens, and we got to do that bit yet, too. So what did I do with my notes? I grabbed the wrong set of notes. This is going to suck. Okay. There's still enough seats, right? We didn't
there's enough seats.
Outdate our seats.
And we think we were doing that same thing we did on Friday where it was like,
yeah, my old one. I'm going to, because I just grabbed this thing, and it's not even what I wanted. My other notes are sitting on my desk still.
I like your time.
Thank you. It's almost time to get rid of it because I've been in 4 places down here this afternoon.
Oh.
I'm going to get it caught. All right. So if I got this straight, we covered vertical incline calculations, right? But we didn't get into or vertical submerged calculations, but we didn't get into the other one, right?
We got into the triangle and the fish tank.
Triangle and the fish tank. Cool. That was on against a steel plate, basically.
Right, we were finding a century, and that's where we stopped. We had 1 century.
That's the best way to describe the drawing.
That thing being a lot of size. I know, right? That's a lot of stuff. It's the loudest thing ever. But, I mean, you lose me, but you can't.
All right, this is the 24th. This is the construction management one. It's this one. Come on, let's go to work. Stop frogging around here. Make sure we're
Just something about these Albany elites,
all right. There we go.
Sorry, Mike.
I just,
50 people. Okay. All right. Yeah, I do actually. Thanks. You have a chauffeur in a country club.
all right. So we now need to deal with. Whoa. Heck were you just doing?
Sorry, my infrastructure doing that at Walmart. Sorry, my family owns a home. He's not that. Not that.
It's okay. You don't have to apologize for having your family own a home. Just help somebody else own a home, too. All right, so incline submerged surfaces. So literally we're going to do Yeah, I did it as an earthen dam.
What is that notation?
Soil. And in concrete, we would do this.
No, we didn't. You don't have to draw diagrams like this in the soils class.
It's engineering. Half of it's artwork. We'll try to imitate it. But yeah, so this one, the little triangles inside, is always concrete. That represents the aggregate.
But incline submerged.
Inclined submerged surfaces. Okay, so with that, let me get rid of this thing because I don't need that. And then the other bit is I should have used a ruler. So I'll use a ruler. Maybe I'll use a ruler. No, it's not going to let me. Fine. And it's still black. Click on blue. I think I need to shut my surface down today. Fine. So we got water over here. We got some height Z. We have a angle theta here, okay, which also, by the way, is the same theta down in here. So all that fun things you learned in geometry are coming to pay off, and you're going to haunt yourselves until you're old and gray if you don't remember those things. All right, and what we're looking at is the water acting on. Oh! Perfect question. Sorry. Oh! I want everybody's.
Should I finish?
You can finish.
Oh.
Yeah. No, sorry. Just watching Leo over here make some of the nicest drawings. It's funny. I love my Surface, but the Surface 8, the pen became sloppy or something on inclines. My old 4, I could draw perfectly straight inclined lines, and I don't know why I can't do it on this one. I usually want to use a ruler, but I didn't want to play with me today. So, all right. So, water. We already know, or you should remember, that water pressure changes as we go down the depth. And there's nothing to deal with volume or anything else that has any issues with that, okay? We are going to look for the forces, though, on this down the road eventually. But here's the question. So, impromptu quiz. We should actually do this and do a little poll and that sort of stuff. I'm not that savvy today. How does the water pressure act on the surface, the inclined surface? Horizontal to the base, perpendicular to the face, or vertically with some other source?
To the face.
To the face. So it's perpendicular to the face. Everybody good? Okay. Because otherwise, we'd have a real mess on our hands. So literally, it's going to act in. It's not going to let me pick pens either. So that's our pressure acting perpendicular to the face. Okay? Everybody good? Okay, so don't forget that one. That's a key concept in what we're going to be doing. All right. Free body diagram time. Ready? Statics will always come back to haunt you, folks. Yep, I want my ruler in the world's worst way. Go away. It's not going away. Something that I did this morning when I was in the interviews with the dean. Just didn't want to shut down properly. Yeah, does that get a little complicated?
Hey.
Why? Don't ask me. All right. So any job worth doing is worth doing right. So there's our inclined surface. Okay? And that's 60 degrees off from there. Actually, I'm going to put it inside so we don't get confused with all the other arrows. Okay? Now, we have point A here, which will be the base, and we got point B up here, which is the surface of the water. Okay? So there's point B up here. All right. Now, I know Dr. Regal likes to have spreadsheets in colors, but I really like to have other things in color. So anyways, we know we're going to be perpendicular to the face here, right? That didn't go, that blue?
Yeah.
Okay. So there's a pressure, right? And we're going to keep going up along this, but I'm going to cheat, okay, just for drawing sakes. So if this is the .30 degrees, so our pressure is going to be doing this the whole time, and it changes with our depths. And just like with a vertical surface, we'd expect it to be less on each of those. So we literally got all our pressures at some depth Z. Okay? Now, just like with a vertical surface that we did the other day, that pressure of that triangle is going to be acting at its centroid. Okay? So from the very bottom of this up, we are going to come up to here, and I'm going to put in F R and I'm going to have an FV.
What's the
FR is the reaction.
No, I understand that. But
Sorry.
like, is there a reason where you place the FR that way, or just kind of put it somewhere in the middle?
It is literally
That's going to be the center right there.
1/3 up. Okay. So the cool thing is, pretty much all we got to deal with is triangles and fluids. We don't really get into any really odd calculations. Okay. So with me so far? All right. All right. So next piece of the grand puzzle. And let's see, I want a different color here.
Is that 1/3 of the length AB or 1/3 of Z?
1/3 of Z, but not the Z you're thinking of.
Right.
Okay, that's all coming up here.
Okay.
All right, let's get this a little higher on the screen so I can draw. So we come off point A and we go up to point B. Okay, and we are Z here is equal to L sine of theta. Okay. Sorry, I did that wrong. I want the L first. L is this distance here. Okay. So this is 1/3 of L off the bottom. All right. Now, I got to get... Oh, we need another color. And just in honor of Dr. Regal, we'll use purple. Yeah. And this is going to get messy, so I'm going to come down here. Z is equal to L sine of theta. Okay. All right, so what's going on here? Ideally, we have two forces that we can come out of this pressure stuff with. I'm going to show you some equations here in a minute. We got all the dimensions that we really need to have. There's one thing missing, though. Anybody thinking about this from a purely static standpoint? So we got a weight of water of that point. All right. Now, does that look like we got all our forces and everything that we could possibly account for, reaction-wise? As long as we're on this planet, it works. Okay. All right. So let's get rid of the ruler here. Let's get back to black. All right. So FV is equal to unit weight times the width times Z. Okay? And then our next one for W is equal to unit weight times the width, L squared over 2 sine theta cosine theta. Okay. Now, we can spend a lot of time on some fun mathematics here. Do you care where sine theta, cosine theta came from?
Where it came from?
Yeah. Like, how to get derived.
You mean like
Mathematically, where did that stupid thing come from?
from law of cosines?
Yeah, it has to deal with a lot of trigonometric functions. Okay, so keep your life simple. You don't need to get into that, but if you're ever interested, I'd be happy to do the math with you. But just know this is the equation. Okay? But it came from realistic mathematics and not somebody just throwing cosine sine down there having a good time. Okay? Otherwise, we could spend a whole hour just doing that. And we don't need to. Okay. All right. So the next thing is we want to find f of r because we need to know the force on that. Oh, I should explain too why we're looking for the force. The force we want to know because we need to figure out how much soil has to be in that earthen dam. So when we build this thing, we're not just guessing. Well, it looks like 5 dump trucks will work. Okay, this isn't flood control where they're sandbagging the wall and they run out of sandbagging. Well, I guess that's all we got. Live with it. And usually the water finds a way to knock it over and go over around it or something. We're building this. This earthen dam is going to be there for the next 100, 200 years. We don't want it washing away. And so how much dirt has to be in there? So we have to find that force. Okay. With me so far on that? Okay. Now, from the standpoint of statics, if I have this force and that force, or I'm sorry, this force and FV, how do I find FR? This is a good time to dust off all the statics that are floating around in the back of your head that haven't seen reality, the light of day. Cool.
Oh, PEMDAS.
Absolutely.
PEMDAS.
Absolutely. Well, you know, so we're looking for V, or we're looking for FR, using FV.
Remember doing that? Right? Pretty cool. Damn, isn't that funny how statics keeps coming back into this thing?
It's in my dreams every night.
Statics is? You doing structural analysis right now, or are you doing statics?
What? Right now?
Yeah.
Right now?
Oh,
Yeah.
not right now, but I mean in
The sequence of my dreams?
yeah.
I don't know anymore.
Engineering, it's just all coming together. I don't know what to do with myself. All right. Now, the other bit is we'd like to know the distance. Oh, I need my ruler again. The only thing I wish the ruler would just lock in at a certain point. We need to know LR now. Yeah, I would like it to freewheel, but I also want it to hit the common ones. Okay, so we got to come up with that distance too. We need to know where that LR is. Okay, so in doing so, LR is equal to 1 over FR Get out of there. Don't want you there. All right. And we're going to do some examples here too. So all this will start making some sense to you shortly. Okay. That is a YR, yep. So we're going to switch from Z's to Y's, still meaning the same vertical height. X's, and how far X comes over from the top surface of the water. Okay. Questions so far? Oh, I forgot to close the other bracket. Sorry. It's because I was fighting with a ruler here. Get out of there. Yeah, there should be another bracket there. Because one bracket's never enough. All right. How are we doing time-wise? Cool, we got lots of time today. Oh, you're so in trouble. All right, so this is your, I'm going to draw this line right there. This is all just the theory back up here. We're going to, oh, this is a good question. I asked this in height construction, so half of you will get it. This is the best way to tackle this elephant. One bite at a time. So we could go right back into submerged inclines, but wouldn't it be nicer to just do some vertical ones first? Just the way the water on top, we enough to deal with all the sine cosines. So we're going to work our way through that ever so gently to the point where you understand. Which reminds me, Wednesday, we're going to do inclined surfaces. Okay. So we're going to submerged surfaces. We're going to do vertical, we're going to do incline. So we'll get some practical experience for this. Another thing I need to tell you is you were part of the guinea pig show that we're doing for SUNY. They wanted to see students in labs on Wednesday from 2 o'clock to 4 o'clock when they're here. You guys are part of the 2:15 tour. So behave yourselves. You get a lot of dignitaries running around. Okay.
And that's lab 3 and 4, right?
Yep, we're going to try and do 3 and 4 together.
So you need to print both handouts.
All right. Let's try one here as an example. So, really? Can't make a 90? Fine. And we are going to be 20 feet below glass window. Oh, and yeah, this one's going to be fun. Salt water. Reminds me, Dr. Regal, remind me after we get done here to tell you about the geologist I watched the other day on the formation of salt issues in the Gulf, on the Gulf Coast. And really cool. I don't remember his name right now, but I got him logged onto YouTube. So it was one of those, YouTube just presented him to me. It's like, I'll watch that. And when I got done, it's like, that's intriguing. All right, so we got a window here that's 18 feet. Okay. All right, now, and you guys need to know something about this because we definitely need the areas out of this. So think about this window sitting in the bottom like so. Oh, get out of there. I'm having way more fun today than I thought with this. 18 feet, yep. So we're 18 feet here, but we go back 16 feet there. Mind you, I would never purposely build this structure. Somebody may want to, but I wouldn't.
Why not?
I don't really care if the whale's over my head and I'm looking at it. And if the glass cracks, I won't be there to appreciate it. So, no, I'm not designing this. But it gets the point across. Okay? So, for.
Oh, that's a question.
Okay. Oh!
There goes the time.
Imagine there's water in this and there's pressure on the glass. If there's a whale in the tank, does that increase the pressure on the glass?
No.
Well, then why does it matter if there's a whale in there?
Because if the glass cracked, the whale's going to come through that hole, and I'm telling you, that whale ain't going to fit. It'll plug up the water, so there's probably a chance of surviving, but the whale's going to be mush. So why doesn't it affect it, though? So a whale floating around in the water, does that change the pressure at all on the water?
Well, I guess not. You just said it was only affected by the depth.
Pressure's only affected by the depth, and the whale doesn't add any extra weight to it because the whale is buoyant. Okay? Same with the fish. Now, we could look at the whale and determine some structures based on that and pressures on the whale. But that's a whole other thing. It's like trying to figure out how a submarine survives. Okay? But in this particular case, nothing to worry about. Okay, what are we going to find? Find force and the center of pressure on the glass. Okay. Oh yeah, this is my favorite example. This is the one that goes step by step. So, guys like logically thinking, here's the way to do this. So, first thing we're going to do is go find the force. Okay. And we're going to use FR because that's our resultant. And we're going to put it in as this. Okay. And the reason I gave you the salt water is 64, because you know that. If you're 62.4, you'd be off by something. But, you know, in the world of engineering, we put factors of safety in. You're probably going to be okay. But you might as well use the right numbers. So, 64. So, 64 pounds per cubic feet. Remember the cubed. We're going to multiply it times Z, our depth, which is 20 feet. And we got our 18 feet times our 16 feet. Okay? So recognize that specific weight times the Z is our pressure, and that the length times the width of the glass is our area that it's acting on, right? No violation of statics there so far, just other than some weird units to get to there. Okay. So, oh yeah, 368,640 pounds. That's a lot of force. Okay. Now, to keep you consistent with the world of engineering and the civil world that you're in, I used to gripe about this, and then I gave up. Okay. So 369 kids. Something you can relate to? Still a lot of water overhead. So if I have a force at the center of that glass, okay, so it'll be 9 feet in from one edge, and then the 16 back, it'll be 8 feet in. That's where the center of that force is. Do we wind up getting a beam reaction that we can calculate? So just think about this for a minute. FR, and we're 18 feet this way, okay, can we calculate the reactions on each end? Yeah. In this case, it's really half of the 369 kips is what that concrete has to resist. Okay? And then you can go even further and start thinking about it from the 16-foot way. All right? Now, I guarantee you the twisting that 90 degrees and calculating the other way, it's going to be stronger just to calculate the 18. But as long as we're having fun in engineering here, no one ever puts the grand picture together. It just pisses me off all my life. What? One 18-foot beam's cool. But when I got a big plate in there, I got to go 16. I got to check that one too. So do your due diligence. Okay? It's going to take you 2 seconds to do the math. But you check the other way to make sure that one's as strong, and then whatever one's the dominant one, design to that one. Okay? Because why make somebody else's hell? Oh, on the 16-foot wide, we only need 4 inches of concrete, while on the 18 inches side, we need 16 feet of concrete. Why would you make them form something in that weird shape? Don't. Okay? Consistency. Make it simple, make it easy, use the largest thing to hold up everything, call it done. Okay? Frog around. Anyways, that's my lecture on statics and ethics. Okay, center. Step 2. I think I already gave this part away, but we're going to have fun here anyways. So we're 16 here, we're 18 feet there. So we're literally right there. Okay. Makes sense to everybody? That one wasn't too hard to calculate. And in the process of biting off big chunks of elephant, this case is easy to take care of that. Yeah, drowning in seawater of, well, you know what happens in aquariums, right? All those animals excrete excrement out into the water, and they actually put divers into those tanks to scrub the algae off the side of the tanks. Okay, so far so good. Let's do, oh yeah. We doing time here? We got good time. All right, no one's ever built this structure in their lifetime in engineering. All right, and the other bit is, might as well get this. And there's our concrete. Kids have all survived the whole harassment in your freshman year. What's the difference between concrete and cement? Yeah, cool. All right, so we literally have got a Z depth here equal to 25 feet. Actually, I know how I got onto that YouTube site. I was looking at Lake Shasta in California. It's getting to the point where enough of that atmospheric river is dumping rain there. That is like 80% right now. And usually at 72%, they start opening the spillways, so they're concerned that the Bureau of Land Management isn't doing their job well. So, all right. Anyway, so then I was like, oh, what's the next one here? That's cool. All right. We need to deal with some things here. And, all right. So remember, it's a triangle. So we're going to come up to 1/3 off the bottom. And that's going to be YR, but we got a YC to deal with. Okay. And, oh, I did some fun with this one. Cool. Sorry. I always told you guys I'm the one more excited about this class than you are. $455 feet in elevation.
Is that water surface there or no?
That's water surface, yep.
Okay.
Our elevation here is 430, which, if all's right, that should be the 25 feet. No. 25 feet. No, it's up here. Wrong place. Elevation here.
Wait, there's no water on the right side of this.
No, there's no water on the right side of this. 30, 25 is 55, right? Yes. Why put it down there? It's just weird. What the hell was I thinking? There's a reason sometimes I don't redo my notes. Okay, so what are we looking for? Find the force or the reaction, depends on, or the resultant, that's the word I want to use. Okay, and the center of pressure, so COP. Oh, and this is fun. COP per foot of dam. New phrase. Ready? Okay. Some days I am, some days I'm not. I just don't have any idea how Wednesday's going to work.
I know.
All right, so equations are things we know. All right. Oh, and it's fresh water too, so we're not going to mess with people's minds on this one. Sorry, that's not a Z, that's a 2. Yeah, so was I. I was looking at it going, what the hell is that Z doing in there? 25 feet. Okay. And, oh, I got to square that one. And we're going by 1 foot. Okay. And we're going to divide this part by 2. Okay. So if you do the math, we got 19,500 pounds per foot, or 19.5 kips per foot. Okay. Well,
The 1 foot.
that's the cool thing. The problem basically says per foot of dam. So for every foot over, that's our force acting on. So what this gets us the ability to do is calculate how much concrete we're going to need down the road per foot and figure out that the stream is 25 feet wide and then calculate it. Okay, otherwise, you need to know the depth area in the back. Now, if no one's ever said this to you before in engineering, I apologize, but when in doubt, you're allowed to assume things. Document it, though. So if they didn't give you the area of the dam or the width across there, and you know it's 25 feet high, you can put in, I assume, 1 foot. Okay? And they can't take you to court for it. Okay? No. Because you wrote down what you assumed. They didn't tell you.
Oh, right.
So, Corps of Engineers, so let's put in a scenario that would make some sense. Corps of Engineers gives you a job as the XYZ construction company or engineering firm. Let's do the engineering firm. Sorry, construction in my head from that earlier. But you're now the engineering firm that's going to do this dam for the Corps of Engineers. Okay, they don't do their own stuff, by the way. They like to think they do, but they don't. It's federal law; they have to contract it out. They do some stuff in house. But anyways, so we get it down to 19.5 kips per foot, and they didn't tell you the width of the dam, nor did you get a chance to go out and actually measure it. It's a good way to come up with a number. And then when you do get an actual measurement, you go out there, okay, I need this many cubic feet of concrete to show up, and this is the way it's going to get done. Okay? Cool. Anyways. All right, center of pressure. All right, so we are going to go get YR, and you're going to come 2/3 down because we have the 25 feet, or you come 1/3 up. Don't care as long as you keep it straight. And make sure you identify things. 8.33 feet. Okay. Or if you're coming where I put the YR here, actually I should do this way. That was my YR. Okay. If I put it down here, then I just want to come back 1/3 up from the 25.
2/3 of 25 is 8.3. That's the whole thing. Yeah, that's what I was thinking.
Oh, somebody do the math. I could have it wrong. Because that wouldn't make sense where I put my YR down here. Yeah. 1/3. Yeah. Cool. And I prefer to do it off the bottom because that's the one thing I know. The bottom is always consistent. The elevation of the water changes, and that would be a problem. Okay. Thank you. Cool. So far, so good? Mm-hmm. Anybody scared to death yet?
No, not yet. It's
okay. Now, Wednesday during lecture, I'll get into inclined surfaces, and then we'll go to the lab that afternoon and mess around with that. The best piece of advice I can give you right now is get the lab instructions out, read them, try to understand them well in advance. Okay? Once we get the group of people the hell out of there, we will actually explain the details. Okay, but it's getting them out of there, and I gotta play in tow behind the president. So as soon as he disappears down, I'm going to wander off real quick into the last thing down here, and then I'm coming back. Okay? So, and I will try to find some time to go through it with you so you know how to get things started. Now we'll get right around there. All right. Any questions on that?
There's no exam.
Oh, yeah, there's no exam on Wednesday, by the way.
If you look on the syllabus, it has that.
Are we, wait a minute, right before you go, are we free for lecture on Wednesday?
No. We have that stupid lunch with them.
Yeah, it's lunch, but, it's 1 o'clock. Yeah, noon. Okay.
Right?
Sure.
Because we have lunch, then we have a
Yeah, we have lunch and that. Okay, so this is going to suck. All right. I think the easiest way for you to do something is this. 2 things. 1, I will pull up last year's vertical or inclined lecture, put that up for you to watch. And then the other bit is, I'll give you an online exam. And don't cheat. It's not like you've got a whole lot of rocket science behind you right now either, but basic water density and fluid mechanics stuff. That way we can get that out of the way.
When you say online
Wednesday
exam, do you mean like exam or just like quiz?
Exam.
Oh, yeah.
So
Look at that. You said I was crazy thinking we'd have it.
no, there was one
You
scheduled,
said I was
but
out of my mind.
it's time-wise, it's almost right. With the SUNY tour, the dog and pony show is not going to be right. But honestly, if you fail this, you need to start over again anyways. I say it that way politely, yeah. There's not a whole lot in this that's going to drive you nuts. So it's density, it's calculating them. So real simple. We'll get it set up. Can you set up a Dropbox for it? And I'll write the exam. Nuts. Forgot about them. Okay. Well, you're going to have a little prep to do to get ready for lab on Wednesday. But once I get done my little dog and pony show through the building, I don't need to follow the rest of Newell and back over to cybersecurity. And so I'll come back to lab and we'll get it working. Okay. But you are part of the show. So dress appropriately. You don't have to put a shirt and tie on or, slacks and a nice blouse. But act like you're decent college students that I think you are. Put it this way. Be as respectful as if your grandmother was showing up to see what you're doing. Okay? Because I don't know what kind of questions they're going to ask or what they're doing. What's that?
Nowadays, that might not mean anything either.
Okay.
Some grandmothers are pretty.
Pretend like it was back in the day when you
Pretend it was like my grandmother showing up that would